Abstract. We introduce our first-generation reasoning models, DeepSeek 10 and DeepSeek 1. DeepSeek 10, a model trained via large-scale reinforcement learning (RL), without supervised fine-tuning (SFT) as a preliminary step, demonstrates remarkable reasoning capabilities. Through RL, DeepSeek 10 naturally emerges with numerous powerful and intriguing reasoning behaviors. However, it encounters challenges such as poor readability and language mixing. To address these issues and further enhance reasoning performance, we introduce DeepSeek 1, which incorporates multi-stage training and cold start data before RL. DeepSeek 1 achieves performance comparable to OpenAI 1 to 1217 on reasoning tasks. To support the research community, we open-source DeepSeek 10, DeepSeek 1, and 6 dense models, 1.5B, 7B, 8B, 14B, 32B, 70B, distilled from DeepSeek 1 based on QWen and Llama. Introduction. In recent years, large language models, LLMs, have been undergoing rapid iteration and evolution, progressively diminishing the gap towards artificial general intelligence, AGI. Recently, post-training has emerged as an important component of the full training pipeline. It has been shown to enhance accuracy on reasoning tasks, align with social values, and adapt to user preferences, all while requiring relatively minimal computational resources against pre-training. In the context of reasoning capabilities, OpenAI S01 series models were the first to introduce inference time scaling by increasing the length of the chain-of-thought reasoning process. This approach has achieved significant improvements in various reasoning tasks, such as mathematics, coding, and scientific reasoning. However, the challenge of effective test time scaling remains an open question for the research community. Several prior works have explored various approaches, including process-based reward models, reinforcement learning, and search algorithms such as Monte Carlo tree search and beam search. However, none of these methods has achieved general reasoning performance comparable to OpenAI S01 series models. In this paper, we take the first step toward improving language model reasoning capabilities using pure reinforcement learning, RL. Our goal is to explore the potential of LLMs to develop reasoning capabilities without any supervised data, focusing on their self-evolution through a pure RL process. Specifically, we use DeepSeek v3 base as the base model and employ GRPO as the RL framework to improve model performance in reasoning. During training, DeepSeek 10 naturally emerged with numerous powerful and interesting reasoning behaviors. After thousands of RL steps, DeepSeek 10 exhibits super performance on reasoning benchmarks. For instance, the pass at 1 score on AIM 2024 increases from 15.6% to 71.0%, and with majority voting, the score further improves to 86.7%, matching the performance of OpenAI 1 to 0912. However, DeepSeek 10 encounters challenges such as poor readability and language mixing. To address these issues and further enhance reasoning performance, we introduce DeepSeek 1, which incorporates a small amount of cold start data and a multi-stage training pipeline. Specifically, we begin by collecting thousands of cold start data to fine-tune the DeepSeek v3 base model. Following this, we perform reasoning-oriented RL like DeepSeek 10. Upon nearing convergence in the RL process, we create new SFT data through rejection sampling on the RL checkpoint, combined with supervised data from DeepSeek v3 in domains such as writing, factual QA, and self-cognition, and then retrain the DeepSeek v3 base model. After fine-tuning with the new data, the checkpoint undergoes an additional RL process, taking into account prompts from all scenarios. After these steps, we obtained a checkpoint referred to as DeepSeek R1, which achieves performance on par with OpenAI 1 to 1217. We further explore distillation from DeepSeek R1 to smaller dense models. Using QN 2.5 to 32B as the base model, direct distillation from DeepSeek R1 outperforms applying RL on it. This demonstrates that the reasoning patterns discovered by larger base models are crucial for improving reasoning capabilities. We open-source the distilled QN and Llama series. Notably, our distilled 14B model outperforms state-of-the-art open-source QWQ32B preview by a large margin, and the distilled 32B and 70B models set a new record on the reasoning benchmarks among dense models. We directly apply RL to the base model without relying on supervised fine-tuning SFT as a preliminary step. This approach allows the model to explore chain of thought, CoT, for solving complex problems, resulting in the development of DeepSeek R10. DeepSeek R10 demonstrates capabilities such as self-verification, reflection, and generating long CoT quotes, marking a significant milestone for the research community. Notably, it is the first open research to validate that reasoning capabilities of LLMs can be incentivized purely through RL, without the need for SFT. This breakthrough paves the way for future advancements in this area. We introduce our pipeline to develop DeepSeek R1. The pipeline incorporates 2 RL stages aimed at discovering improved reasoning patterns and aligning with human preferences, as well as 2 SFT stages that serve as the seed for the model's reasoning and non-reasoning capabilities. We believe the pipeline will benefit the industry by creating better models. We demonstrate that the reasoning patterns of larger models can be distilled into smaller models, resulting in better performance compared to the reasoning patterns discovered through RL on small models. The open-source DeepSeek R1, as well as its API, will benefit the research community to distill better smaller models in the future. Using the reasoning data generated by DeepSeek R1, we fine-tuned several dense models that are widely used in the research community. The evaluation results demonstrate that the distilled smaller dense models perform exceptionally well on benchmarks. DeepSeek R1 Distill QN7B achieves 55.5% on AIM 2024, surpassing QWQ32B preview. Additionally, DeepSeek R1 Distill QN32B scores 72.6% on AIM 2024, 94.3% on Math 500, and 57.2% on Live Code Bench. These results significantly outperform previous open-source models and are comparable to O1 Mini. We open-source distilled 1.5B, 7B, 8B, 14B, 32B, and 70B checkpoints based on QN 2.5 and Llama 3 series to the community. Reasoning tasks. 1. DeepSeek R1 achieves a score of 79.8% pass at 1 on AIM 2024, slightly surpassing OpenAI 1 to 1217. On Math 500, it attains an impressive score of 97.3%, performing on par with OpenAI 1 to 1217 and significantly outperforming other models. 2. On coding-related tasks, DeepSeek R1 demonstrates expert level in code competition tasks, as it achieves 2029 a low rating on Codeforces, outperforming 96.3% human participants in the competition. For engineering-related tasks, DeepSeek R1 performs slightly better than DeepSeek V3, which could help developers in real-world tasks. Knowledge. On benchmarks such as MMLU MMLU Pro, and GPQA Diamond, DeepSeek R1 achieves outstanding results, significantly outperforming DeepSeek V3 with scores of 90.8% on MMLU, 84.0% on MMLU Pro, and 71.5% on GPQA Diamond. While its performance is slightly below that of OpenAI 1 to 1217 on these benchmarks, DeepSeek R1 surpasses other closed-source models, demonstrating its competitive edge in educational tasks. On the factual benchmark Simple QA, DeepSeek R1 outperforms DeepSeek V3, demonstrating its capability in handling fact-based queries. A similar trend is observed where OpenAI 1 surpasses 4.0 on this benchmark. Others, DeepSeek R1 also excels in a wide range of tasks, including creative writing, general question answering, editing, summarization, and more. It achieves an impressive length-controlled win rate of 87.6% on Alpaca, Eval 2.0, and a win rate of 92.3% on Arena Hard, showcasing its strong ability to intelligently handle non-exam-oriented queries. Additionally, DeepSeek R1 demonstrates outstanding performance on tasks requiring long context understanding, substantially outperforming DeepSeek V3 on long context benchmarks. Approach. Previous work has heavily relied on large amounts of supervised data to enhance model performance. In this study, we demonstrate that reasoning capabilities can be significantly improved through large-scale reinforcement learning RL, even without using supervised fine-tuning SFT as a cold start. Furthermore, performance can be further enhanced with the inclusion of a small amount of cold start data. In the following sections, we present 1. DeepSeek R10, which applies RL directly to the base model without any SFT data, and 2. DeepSeek R1, which applies RL starting from a checkpoint fine-tuned with thousands of long chain of thought, CoT, examples. 3. Distill the reasoning capability from DeepSeek R1 to small dense models. Reinforcement learning has demonstrated significant effectiveness in reasoning tasks, as evidenced by our previous works. However, these works heavily depended on supervised data, which are time-intensive to gather. In this section, we explore the potential of LLMs to develop reasoning capabilities without any supervised data, focusing on their self-evolution through a pure reinforcement learning process. We start with a brief overview of our RL algorithm, followed by the presentation of some exciting results, and hope this provides the community with valuable insights. In order to save the training costs of RL, we adopt Group Relative Policy Optimization, GRPO, which forgoes the critic model that is typically the same size as the policy model and estimates the baseline from group scores instead. Specifically, for each question, GRPO samples a group of outputs from the old policy and then optimizes the policy model by maximizing the following objective: where and are hyperparameters, and is the advantage, computed using a group of rewards corresponding to the outputs within each group. The reward is the source of the training signal, which decides the optimization direction of RL. To train DeepSeek R10, we adopt a rule-based reward system that mainly consists of two types of rewards: accuracy rewards. The accuracy reward model evaluates whether the response is correct. For example, in the case of math problems with deterministic results, the model is required to provide the final answer in a specified format, e.g., within a box, enabling reliable rule-based verification of correctness. Similarly, for LEET code problems, a compiler can be used to generate feedback based on predefined test cases. Format rewards. In addition to the accuracy reward model, we employ a format reward model that enforces the model to put its thinking process between think and /think tags. We do not apply the outcome or process neural reward model in developing DeepSeek R10. because we find that the neural reward model may suffer from reward hacking in the large-scale reinforcement learning process, and retraining the reward model needs additional training resources, and it complicates the whole training pipeline. To train DeepSeek R10, we begin by designing a straightforward template that guides the base model to adhere to our specified instructions. As depicted in Table 1, this template requires DeepSeek R10 to first produce a reasoning process, followed by the final answer. We intentionally limit our constraints to this structural format, avoiding any content-specific biases, such as mandating reflective reasoning or promoting particular problem-solving strategies, to ensure that we can accurately observe the model's natural progression during the RL process. Figure 2 depicts the performance trajectory of DeepSeek R10 on the AIM 2024 benchmark throughout the RL training process. As illustrated, DeepSeek R10 demonstrates a steady and consistent enhancement in performance as the RL training advances. Notably, the average pass at 1 score on AIM 2024 shows a significant increase, jumping from an initial 15.6% to an impressive 71.0%, reaching performance levels comparable to OpenAI 01 to 0912. This significant improvement highlights the efficacy of our RL algorithm in optimizing the model's performance over time. Table 2 provides a comparative analysis between DeepSeek R10 and OpenAI S01 to 0912 models across a variety of reasoning-related benchmarks. The findings reveal that RL empowers DeepSeek R10 to attain robust reasoning capabilities without the need for any supervised fine-tuning data. This is a noteworthy achievement, as it underscores the model's ability to learn and generalize effectively through RL alone. Additionally, the performance of DeepSeek R10 can be further augmented through the application of majority voting. For example, when majority voting is employed on the AIM benchmark, DeepSeek R10's performance escalates from 71.0% to 86.7%, thereby exceeding the performance of OpenAI 01 to 0912. The ability of DeepSeek R10 to achieve such competitive performance, both with and without majority voting, highlights its strong foundational capabilities and its potential for further advancements in reasoning tasks. The self-evolution process of DeepSeek R10 is a fascinating demonstration of how RL can drive a model to improve its reasoning capabilities autonomously. By initiating RL directly from the base model, we can closely monitor the model's progression without the influence of the supervised fine-tuning stage. This approach provides a clear view of how the model evolves over time, particularly in terms of its ability to handle complex reasoning tasks. As depicted in Figure 3, the thinking time of DeepSeek R10 shows consistent improvement throughout the training process. This improvement is not the result of external adjustments, but rather an intrinsic development within the model. DeepSeek R10 naturally acquires the ability to solve increasingly complex reasoning tasks by leveraging extended test time computation. This computation ranges from generating hundreds to thousands of reasoning tokens, allowing the model to explore and refine its thought processes in greater depth. One of the most remarkable aspects of this self-evolution is the emergence of sophisticated behaviors as the test time computation increases. Behaviors such as reflection, where the model revisits and reevaluates its previous steps, and the exploration of alternative approaches to problem-solving arise spontaneously. These behaviors are not explicitly programmed, but instead emerge as a result of the model's interaction with the reinforcement learning environment. This spontaneous development significantly enhances DeepSeek R10's reasoning capabilities, enabling it to tackle more challenging tasks with greater efficiency and accuracy. A particularly intriguing phenomenon observed during the training of DeepSeek R10 is the occurrence of an aha moment. This moment, as illustrated in Table 3, occurs in an intermediate version of the model. During this phase, DeepSeek R10 learns to allocate more thinking time to a problem by re-evaluating its initial approach. This behavior is not only a testament to the model's growing reasoning abilities, but also a captivating example of how reinforcement learning can lead to unexpected and sophisticated outcomes. This moment is not only an aha moment for the model, but also for the researchers observing its behavior. It underscores the power and beauty of reinforcement learning. Rather than explicitly teaching the model on how to solve a problem, we simply provide it with the right incentives, and it autonomously develops advanced problem-solving strategies. The aha moment serves as a powerful reminder of the potential of RL to unlock new levels of intelligence in artificial systems, paving the way for more autonomous and adaptive models in the future. Although DeepSeek R10 exhibits strong reasoning capabilities and autonomously develops unexpected and powerful reasoning behaviors, it faces several issues. For instance, DeepSeek R10 struggles with challenges like poor readability and language mixing. To make reasoning processes more readable and share them with the open community, we explore DeepSeek R1, a method that utilizes RL with human-friendly cold start data. Inspired by the promising results of DeepSeek R10, two natural questions arise. 1. Can reasoning performance be further improved or convergence accelerated by incorporating a small amount of high-quality data as a cold start? 2. How can we train a user-friendly model that not only produces clear and coherent chains of thought, (CoT), but also demonstrates strong general capabilities? To address these questions, we design a pipeline to train DeepSeek R1. The pipeline consists of 4 stages, outlined as follows. Unlike DeepSeek R10, to prevent the early unstable cold start phase of RL training from the base model, for DeepSeek R1, we construct and collect a small amount of long CoT data to fine-tune the model as the initial RL actor. To collect such data, we have explored several approaches, using few-shot prompting with a long CoT as an example, directly prompting models to generate detailed answers with reflection and verification, gathering DeepSeek R10 outputs in a readable format, and refining the results through post-processing by human annotators. In this work, we collect thousands of cold start data to fine-tune the DeepSeek v3 base as the starting point for RL. Compared to DeepSeek R10, the advantages of cold start data include readability. A key limitation of DeepSeek R10 is that its content is often not suitable for reading. Responses may mix multiple languages or lack markdown formatting to highlight answers for users. In contrast, when creating cold start data for DeepSeek R1, we design a readable pattern that includes a summary at the end of each response and filters out responses that are not reader-friendly. Here, we define the output format as Special Token Reasoning Process Special Token Summary, where the reasoning process is the CoT for the query, and the summary is used to summarize the reasoning results. Potential. By carefully designing the pattern for cold start data with human priors, we observe better performance against DeepSeek R10. We believe the iterative training is a better way for reasoning models. After fine-tuning DeepSeek v3 base on the cold start data, we apply the same large-scale reinforcement learning training process as employed in DeepSeek R10. This phase focuses on enhancing the model's reasoning capabilities, particularly in reasoning-intensive tasks such as coding, mathematics, science, and logic reasoning, which involve well-defined problems with clear solutions. During the training process, we observe that CoT often exhibits language mixing, particularly when RL prompts involve multiple languages. To mitigate the issue of language mixing, we introduce a language consistency reward during RL training, which is calculated as the proportion of target language words in the CoT. Although ablation experiments show that such alignment results in a slight degradation in the Model's performance, this reward aligns with human preferences, making it more readable. Finally, we combine the accuracy of reasoning tasks and the reward for language consistency by directly summing them to form the final reward. We then apply RL training on the fine-tuned model until it achieves convergence on reasoning tasks. When reasoning-oriented RL converges, we utilize the resulting checkpoint to collect SFT, supervised fine-tuning, data for the subsequent round. Unlike the initial cold start data, which primarily focuses on reasoning, this stage incorporates data from other domains to enhance the Model's capabilities in writing, role-playing, and other general-purpose tasks. Specifically, we generate the data and fine-tune the model as described below. We curate reasoning prompts and generate reasoning trajectories by performing rejection sampling from the checkpoint from the above RL training. In the previous stage, we only included data that could be evaluated using rule-based rewards. However, in this stage, we expand the dataset by incorporating additional data, some of which use a generative reward model by feeding the ground truth and model predictions into DeepSeek v3 for judgment. Additionally, because the model output is sometimes chaotic and difficult to read, we have filtered out chain of thought with mixed languages, long paragraphs, and code blocks. For each prompt, we sample multiple responses and retain only the correct ones. In total, we collect about 600K reasoning-related training samples. For non-reasoning data, such as writing, factual QA, self-cognition, and translation, we adopt the DeepSeek v3 pipeline and reuse portions of the SFT dataset of DeepSeek v3. For certain non-reasoning tasks, we call DeepSeek v3 to generate a potential chain of thought before answering the question by prompting. However, for simpler queries, such as hello, we do not provide a CoT in response. In the end, we collected a total of approximately 200K training samples that are unrelated to reasoning. We fine-tuned DeepSeek v3 base for 2 epochs using the above curated dataset of about 800K samples. To further align the model with human preferences, we implement a secondary reinforcement learning stage aimed at improving the model's helpfulness and harmlessness, while simultaneously refining its reasoning capabilities. Specifically, we train the model using a combination of reward signals and diverse prompt distributions. For reasoning data, we adhere to the methodology outlined in DeepSeek 10, which utilizes rule-based rewards to guide the learning process in math, code, and logical reasoning domains. For general data, we resort to reward models to capture human preferences in complex and nuanced scenarios. We build upon the DeepSeek v3 pipeline and adopt a similar distribution of preference pairs and training prompts. For helpfulness, we focus exclusively on the final summary, ensuring that the assessment emphasizes the utility and relevance of the response to the user while minimizing interference with the underlying reasoning process. For harmlessness, we evaluate the entire response of the model, including both the reasoning process and the summary, to identify and mitigate any potential risks, biases, or harmful content that may arise during the generation process. Ultimately, the integration of reward signals and diverse data distributions enables us to train a model that excels in reasoning while prioritizing helpfulness and harmlessness. To equip more efficient smaller models with reasoning capabilities like DeepSeek R1, we directly fine-tuned open-source models like QWen and Llama using the 800K samples curated with DeepSeek R1, as detailed in 2.3.3. Our findings indicate that this straightforward distillation method significantly enhances the reasoning abilities of smaller models. The base models we use here are QWen 2.5 Math 1.5b, QWen 2.5 Math 7b, QWen 2.5 to 14b, QWen 2.5 to 32b, Llama 3.1 to 8b, and Llama 3.3 to 70b instruct. We select Llama 3.3 because its reasoning capability is slightly better than that of Llama 3.1. For distilled models, we apply only SFT and do not include an RL stage, even though incorporating RL could substantially boost model performance. Our primary goal here is to demonstrate the effectiveness of the distillation technique, leaving the exploration of the RL stage to the broader research community. Experiment. We evaluate models on MMLU, MMLU Redux, MMLU Pro, C-eval, and CMMLU. If eval, frames, GPQA Diamond, Simple QA, C Simple QA, SWE Bench Verified, Aider 111 https://Aider chat. Live Code Bench 2024 to 08, 2025 to 01. Codeforces 222 https://codeforces.com. Chinese National High School Mathematics Olympiad, CNMO 2024, 333 https://www.cms.org/home/comp/sid/12 HTML. And American Invitational Mathematics Examination 2024, AIM 2024. In addition to standard benchmarks, we also evaluate our models on open-ended generation tasks using LLMs as judges. Specifically, we adhere to the original configurations of Alpaca, Eval 2.0, and ArenaHard, which leverage GPT-4 Turbo 1106 as judges for pairwise comparisons. Here, we only feed the final summary to evaluation to avoid the length bias. For distilled models, we report representative results on AIM 2024, Math 500, GPQA Diamond, Codeforces, and Live Code Bench. Following the setup in DeepSeek v3, standard benchmarks such as MMLU, DROP, GPQA Diamond, and Simple QA are evaluated using prompts from the Simple Evals framework. For MMLU Redux, we adopt the zero-eval prompt format in a zero-shot setting. In terms of MMLU Pro, C-eval, and CLUWSC, since the original prompts are few-shot, we slightly modify the prompt to the zero-shot setting. The CO-T in few-shot may hurt the performance of DeepSeek R1. Other datasets follow their original evaluation protocols with default prompts provided by their creators. For code and math benchmarks, the Human EvalMol dataset covers 8 mainstream programming languages: Python, Java, C++, C#, JavaScript, TypeScript, PHP, and Bash. Model performance on Live Code Bench is evaluated using CO-T format, with data collected between August 2024 and January 2025. The Codeforces dataset is evaluated using problems from 10 Div.2 contests, along with expert-crafted test cases, after which the expected ratings and percentages of competitors are calculated. SWE Bench verified results are obtained via the agentless framework. Aider-related benchmarks are measured using a diff format. DeepSeek R1 outputs are capped at a maximum of 32,768 tokens for each benchmark. We conduct comprehensive evaluations against several strong baselines, including DeepSeek v3, Claude Sonnet 3.5 to 1022, GPT 400513, OpenAI o1 Mini, and OpenAI o1 to 1217. Since accessing the OpenAI o1 to 1217 API is challenging in mainland China, we report its performance based on official reports. For distilled models, we also compare the open-source model QWQ32B Preview. We set the maximum generation length to 32,768 tokens for the models. We found that using greedy decoding to evaluate long-output reasoning models results in higher repetition rates and significant variability across different checkpoints. Therefore, we default to pass at evaluation and report pass at 1 using a non-zero temperature. Specifically, we use a sampling temperature of and a top value of to generate responses, typically between and, depending on the test set size for each question. Pass at 1 is then calculated as where denotes the correctness of the TH response. This method provides more reliable performance estimates. For AIM 2024, we also report consensus majority vote results using samples, denoted as. For education-oriented knowledge benchmarks such as MMLU, MMLU Pro, and GPQA Diamond, DeepSeek R1 demonstrates superior performance compared to DeepSeek v3. This improvement is primarily attributed to enhanced accuracy in STEM-related questions, where significant gains are achieved through large-scale reinforcement learning. Additionally, DeepSeek R1 excels on frames, a long context-dependent QA task, showcasing its strong document analysis capabilities. This highlights the potential of reasoning models in AI-driven search and data analysis tasks. On the factual benchmark Simple QA, DeepSeek R1 outperforms DeepSeek v3, demonstrating its capability in handling fact-based queries. A similar trend is observed where OpenAI o1 surpasses GPT-4o on this benchmark. However, DeepSeek R1 performs worse than DeepSeek v3 on the Chinese Simple QA benchmark, primarily due to its tendency to refuse answering certain queries after safety RL. Without safety RL, DeepSeek R1 could achieve an accuracy of over 70%. DeepSeek R1 also delivers impressive results on IF-eval, a benchmark designed to assess a model's ability to follow format instructions. These improvements can be linked to the inclusion of instruction-following data during the final stages of supervised fine-tuning, SFT, and RL training. Furthermore, remarkable performance is observed on Alpaca, Eval 2.0, and Arena Hard, indicating DeepSeek R1's strengths in writing tasks and open domain question answering. Its significant outperformance of DeepSeek v3 underscores the generalization benefits of large-scale RL, which not only boosts reasoning capabilities, but also improves performance across diverse domains. Moreover, the summary lengths generated by DeepSeek R1 are concise, with an average of 689 tokens on Arena Hard and 2,218 characters on Alpaca, Eval 2.0. This indicates that DeepSeek R1 avoids introducing length bias during GPT-based evaluations, further solidifying its robustness across multiple tasks. On math tasks, DeepSeek R1 demonstrates performance on par with OpenAI o1 to 1217, surpassing other models by a large margin. A similar trend is observed on coding algorithm tasks, such as live code bench and codeforces, where reasoning-focused models dominate these benchmarks. On engineering-oriented coding tasks, OpenAI o1 to 1217 outperforms DeepSeek R1 on Aider, but achieves comparable performance on SWE verified. we believe the engineering performance of DeepSeek R1 will improve in the next version, as the amount of related RL training data currently remains very limited. As shown in Table 5, simply distilling DeepSeek R1's outputs enables the efficient DeepSeek R1 to 7B, i.e. DeepSeek R1 distill QN7B, abbreviated similarly below, to outperform non-reasoning models like GPT-400513 across the board. DeepSeek R1 to 14B surpasses QWQ32B preview on all evaluation metrics, while DeepSeek R1 to 32B and DeepSeek R1 to 70B significantly exceed O1 mini on most benchmarks. These results demonstrate the strong potential of distillation. Additionally, we found that applying RL to these distilled models yields significant further gains. We believe this warrants further exploration, and therefore present only the results of the simple SFT distilled models here. Discussion. In Section 3.2, we can see that by distilling DeepSeek R1, the small model can achieve impressive results. However, there is still one question left. Can the model achieve comparable performance through the large-scale RL training discussed in the paper without distillation? To answer this question, we conduct large-scale RL training on QN32B base using math, code, and STEM data, training for over 10K steps, resulting in DeepSeek R10 QN32B. The experimental results, shown in Table 6, demonstrate that the 32B base model, after large-scale RL training, achieves performance on par with QWQ32B preview. However, DeepSeek R1 distill QN32B, which is distilled from DeepSeek R1, performs significantly better than DeepSeek R10 QN32B across all benchmarks. Therefore, we can draw two conclusions. First, distilling more powerful models into smaller ones yields excellent results, whereas smaller models relying on the large-scale RL mentioned in this paper require enormous computational power and may not even achieve the performance of distillation. Second, while distillation strategies are both economical and effective, advancing beyond the boundaries of intelligence may still require more powerful base models and larger-scale reinforcement learning. In the early stages of developing DeepSeek R1, we also encountered failures and setbacks along the way. We share our failure experiences here to provide insights, but this does not imply that these approaches are incapable of developing effective reasoning models. PRM is a reasonable method to guide the model toward better approaches for solving reasoning tasks. However, in practice, PRM has three main limitations that may hinder its ultimate success. First, it is challenging to explicitly define a fine-grained step in general reasoning. Second, determining whether the current intermediate step is correct is a challenging task. Automated annotation using models may not yield satisfactory results, while manual annotation is not conducive to scaling up. Third, once a model-based PRM is introduced, it inevitably leads to reward hacking, and retraining the reward model needs additional training resources, and it complicates the whole training pipeline. In conclusion, while PRM demonstrates a good ability to re-rank the top-N responses generated by the model or assist in guided search, its advantages are limited compared to the additional computational overhead it introduces during the large-scale reinforcement learning process in our experiments. Inspired by AlphaGo and AlphaZero, we explored using Monte Carlo tree search, MCTS, to enhance test time compute scalability. This approach involves breaking answers into smaller parts to allow the model to explore the solution space systematically. To facilitate this, we prompt the model to generate multiple tags that correspond to specific reasoning steps necessary for the search. For training, We first use collected prompts to find answers via MCTS guided by a pre-trained value model. Subsequently, we use the resulting question-answer pairs to train both the actor model and the value model, iteratively refining the process. However, this approach encounters several challenges when scaling up the training. First, unlike chess, where the search space is relatively well-defined, token generation presents an exponentially larger search space. To address this, we set a maximum extension limit for each node, but this can lead to the model getting stuck in local optima. Second, the value model directly influences the quality of generation since it guides each step of the search process. Training a fine-grained value model is inherently difficult, which makes it challenging for the model to iteratively improve. While AlphaGo's core success relied on training a value model to progressively enhance its performance, this principle proves difficult to replicate in our setup due to the complexities of token generation. In conclusion, while MCTS can improve performance during inference when paired with a pre-trained value model, iteratively boosting model performance through self-search remains a significant challenge. Conclusion, limitations, and future work. In this work, we share our journey in enhancing model reasoning abilities through reinforcement learning. DeepSeek R10 represents a pure RL approach without relying on cold start data, achieving strong performance across various tasks. DeepSeek R1 is more powerful, leveraging cold start data alongside iterative RL fine-tuning. Ultimately, DeepSeek R1 achieves performance comparable to OpenAI 01 to 1217 on a range of tasks. We further explore distillation, the reasoning capability to small dense models. We use DeepSeek R1 as the teacher model to generate 800K training samples and fine-tune several small dense models. The results are promising. DeepSeek R1 Distill QN 1.5b outperforms GPT-4o and Claude 3.5 Sonnet on math benchmarks with 28.9% on AIM and 83.9% on math. Other dense models also achieve impressive results, significantly outperforming other instruction-tuned models based on the same underlying checkpoints. In the future, we plan to invest in research across the following directions for DeepSeek R1. General capability. Currently, the capabilities of DeepSeek R1 fall short of DeepSeek v3 in tasks such as function calling, multi-turn, complex role-playing, and JSON output. Moving forward, we plan to explore how long Co-T can be leveraged to enhance tasks in these fields. Language mixing. DeepSeek R1 is currently optimized for Chinese and English, which may result in language mixing issues when handling queries in other languages. For instance, DeepSeek R1 might use English for reasoning and responses, even if the query is in a language other than English or Chinese. We aim to address this limitation in future updates. Prompting engineering. When evaluating DeepSeek R1, we observe that it is sensitive to prompts. Few-shot prompting consistently degrades its performance. Therefore, we recommend users directly describe the problem and specify the output format using a zero-shot setting for optimal results. Software engineering tasks. Due to the long evaluation times, which impact the efficiency of the RL process, large-scale RL has not been applied extensively in software engineering tasks. As a result, DeepSeek R1 has not demonstrated a huge improvement over DeepSeek v3 on software engineering benchmarks. Future versions will address this by implementing rejection sampling on software engineering data or incorporating asynchronous evaluations during the RL process to improve efficiency.